Hello, my name is Kamilla. I'm working as a part of a team in Institute of High Current Electronics in Tomsk. And today I'm here to present you and to talk about the balance control of thermal impact on metal materials using the electron source with plasma cathode. So, the main reasons why we need this thermal impact on different materials is to increase the properties of such different materials, metal, composites, and alloys. And for that purposes are widely used electron sources, especially in particular electron source with plasma cathodes. Moreover, using them, it is able to not only increase the properties of materials, but also nanostructure the surface, polishing the surface, also the mixing the material. My purpose of this work was to demonstrate the possibility of controlling the surface temperature using electron source with plasma cathode based on a low pressure arc discharge. So, equipment that we use in our study was electron source called SOLO. The main advantage of using such electron source is actually its possibility to control the main parameters of electron beam that are also presented on a slide here. In a wide range, smoothly and independently from each other. The construction of this electron source presented on the slide. So initiating of electron beam starts from there. Initiating discharge is ignited between hollow electrode and cathode. Then the main arc discharge burning between cathode and hollow anode. Constant accelerating voltage is applied between emission electrode and extracting electrode. Extracted electrons are transported in a drift tube in the magnetic fields of two coils to the collector. On the collector are placed our specimen of materials that we irradiate. So, on the slide you can see that actually the depth of electron penetration is about 1 micrometer, so it's very small. According to the depth of melting, according to the depth of melted layer. So here you can see the structure of irradiated material. Also, the diameter of electron beam could reach from 40 to 50 millimeters. In general, the process of irradiation of the surface of materials could be described into three main points. First of all, the surface of the material starts melting, then the waste starts evaporate from the surface, as well as a little bit of material itself also starts to evaporate, and finally, after some time of irradiation, we get modified structure. That actually leads to effects of surface smoothing, crystal structure modification, and surface hardening. In our research, we have studied the silylamine. Silylamine is an alloy of aluminum and silicon, and actually there could be three types of this alloy. It depends on how much silicon in it you have. The higher the amount of silicon, the higher the hardness of the material. But at the same time, it comes the problems with the structure, especially with the hyperelectric silylamine because of those huge particles of silicon. That is why we need this electron beam treatment. By the way, besides the high hardness, there are also a lot of great properties of the materials, such as low specific weight, high casting properties, high wear resistance. And because of those properties, it is widely used for making the pistons and plane bearings that are also presented on the slide. Here you can see the oscillograms of discharge current, of the current of the beam itself, and the oscillogram of accelerating voltage. And according to that, we calculated the power during the pulse. So actually, the recent modernization of power supply of electron source allowed us to change the power during the pulse, during one pulse, in a way that we need. So we can get the profile, the different profiles of temperature, increasing and decreasing. And that result we get by controlling the current of the discharge. Here you can see the setup of our experiment. On the on the two-axis table manipulator table, the specimen of silicon material are placed. The temperature of the surface is measured by infrared, high-speed infrared parameter, which is connected via the flexible waveguide to the it is connected to the lens, which is actually in the vacuum chamber, but it covered with the silica glass in order to keep the parameter at the atmospheric pressure. So, with the help of table manipulator, we can move the specimen of silicon to the proper position. Here you can see the photograph of the chamber from the inside. Here you can see the experimental results. So actually the idea was to show that it is possible to control the temperature of the surface, and we decided to keep the temperature of the surface during some time. Here you can see the oscillogram of discharge current, beam current, and accelerating voltage, as well as how temperature behaved during the pulse. The second regime that here the temperature was kept at around 600 degrees, around the melting temperature of the silicon. The next mode that we have chosen is also keeping the temperature after. So for the first time, we were irradiate the material during the first 200 microseconds with the rectangular form of the current, and then just keeping the surface of the temperature, but now during the much higher rate of the temperature at 1000. But then we decided to figure out what would be if we compare the results of irradiating the surface just in these 200 microseconds, then to keep the temperature during the first 400 microseconds, and then during the 1 millisecond. Here you can see the brief description of those modes. So we decided to figure out, is actually there any difference between the classic regime that we studied at our institute and between the mode with keeping the temperature. And here you can see the results that we get. The diagram shows the result of measurement of microhardness and wear rate corresponding to the regimes. So here is the number. Here is microhardness and wear rate for initial specimen that was not irradiated by electron beam, and you can see that after first 200 microseconds, the microhardness increases almost to 2 times, and the wear rate is decreased almost to 3 times. But then after keeping the temperature, we see that results getting better, and the higher the time that we keep this temperature, the better result we get. After that, we decided to conduct numerical calculations. On the slide, you can see the model that describes the temperature field. This equation describes the whole processes. Also, here you can see the description of each part. The thermophysical coefficients are presented on the slide for silicon. And also it should be noted that this function is actually used to describe the two-phase zone of solid and liquid. Here you can see the result of numerical simulation. So we were using the measured current and voltage, and then just calculated the power. Then we used the power and calculated the results of temperature. And you can see that calculated one and experimental one are actually shows the great agreement between each other. So that is why we can say that it's actually the model actually in a good way describes the whole process. But in order to get rid of those pulsations, we decided to take the average amount of power during the pulse, and then here you can see the profile of temperature that we finally get. And also we've calculated the depth of melted material, and it reached to the 80 micrometers. In conclusion, I want to say that we, in our work, wanted to show you this possibility of using our electron source for keeping the surface temperature, and that actually keeping the surface temperature shows the good results for materials properties. And now we can also conduct numerical calculations for different materials, because it showed the great agreement. So thank you very much for your attention.